So the first thing we're going to talk about are the procedures that you're going to go through when you are solving these applied max and min problems. And then we're going to talk about some key words that you might want to look for, because we won't always say maximum and minimum. So applied max and min problems are often known as optimization problems. Okay, and you're going to optimize whether you're looking for the smallest amount of material to use because you are environmentally friendly, or you want to maximize the amount of space that you have, I don't know, in your yard by fencing in for your dog, something like that. So these are the procedures for solving, okay? And sometimes these may or may not apply, it just depends on the problem. So I'll just highlight all these steps here. So the first thing you want to do, if you can, is draw an appropriate figure, okay? A lot of you did not do this with respect to the related rates, and some of you may have found it difficult. But if you're talking about a rectangle or a triangle or anything like that, you want to draw the figure so you can see what is really happening. A lot of times you think you can see it in your head, and I can't see what's in your head. So you should practice putting it on paper. You also want to make sure you label all the quantities that are relevant to the problem. This goes back to related rates. If you know what dV/dt is, write it down. Okay, don't just leave it in there. Then you need to identify or find the formula that you want to maximize or minimize. Okay, so sometimes it's going to be an area, sometimes it's a perimeter, it might be a combination of the two, a surface area, so you got to take a look at what you're given. Okay, a lot of times, like I said, you've got area, perimeter, it could be cost, distance. Okay, there's a lot of different examples. It could go on and on, but those are just some examples. So using the conditions stated in the problem, you want to eliminate variables and make sure you express the quantities to be either maximized or minimized as one variable. So you don't want to have more than one variable. So here it says eliminate variables. Okay, and you want to make sure that it's in one variable, meaning you can't have both x's and y's, okay, or no h's and t's. Like it's got to be one variable. So you'll probably be making a substitution of one in terms of another. A lot of times too in the problem you'll be given an interval, meaning there's going to be some kind of physical restrictions in the problem. You need to make sure that you identify this, and then how do we find a max or min? What do we have to do?
Critical number.
How do you find the critical numbers? Yes, you're going to use the derivative, okay? So it's not if applicable, because this is definitely going to apply. The techniques that you're going to use, okay, to obtain the max and the min is either going to be the first or the second derivative test. Okay, so it just depends on the problem. All right, so let's talk about some of the words that we could use. That would be, and I'm going to put it up here since we don't have a whole lot of room, synonyms for maximize. Give me some synonyms to, like, for maximum or maximize. Peak. Okay. What else?
Apex.
How would you put that into a word problem? Find the apex. I mean, I'm not saying that they're not, but what's it like? Think even simpler. Maximize. Biggest. What else?
The greatest.
Oh my gosh. Greatest. What else?
Largest.
Largest. Anything else?
Hugest.
Okay. I don't know if that's a word, so I'm not going to write that down. Hugest.
Superior.
Think about distance too. What's another word you could? Longest. Okay.
Farthest?
Yeah. Is it farthest or furthest?
Furthest.
Oh my. It's what? Farthest. All right, we'll stick with farthest. I'm not in English. Okay, so you guys get the idea. According to, I don't know who that was, Shakespeare. Furthest, I don't know. Okay, what about synonyms for minimize? Say again? Smallest. I can't hear you. What else?
Weakest.
Shortest. I don't know. I'm just going to keep moving.
Lowest.
Lowest. Least.
So,
Cheapest.
cheap. Oh, yeah.
Least expensive, right? So cheapest. I don't know. It's just a suggestion. Okay. Closest, maybe?
Wait, what was all for the least?
I don't know.
I think we should add expensivest to the top.
No, expensivest.
If you can fit that in there, he says,
Expensivest?
I would say the most expensive, but why would you want to, what's the most expensive way that you could do this? Why would you want to do that? Like, but you go with Jay.
You want to estimate how
Okay,
much it might
so you guys get the idea. Yes? Hello?
Yes.
Okay, then what's the most difficult way to do this problem? Okay, so we're going to start with something pretty simple here. Okay, and sometimes we're just going to have to figure out just a general formula. The very first one that we're doing just kind of gets us in the algebraic realm. So here it says find a positive number such that the sum of the number and its reciprocal is as small as possible. So I'm going to go through and highlight some of these keywords. So first of all, we want a positive number. Okay, so we already know, okay, if I get any negative answers, can't use those. What else can I use? If I'm looking for a positive number. Oh, 0. So just, you got to think about that, okay, so you can eliminate some choices, such that the sum, okay, of whatever that number is and its reciprocal is as small as possible. So what am I going to do here? If I'm looking for their sum to be as small as possible, what are we looking for? Yes, we're trying to minimize or find the minimum. Okay, so first of all, in all of these problems, you're going to have to take the derivative of some kind, right? But we don't even have an equation to deal with, so we need to find one. So we're going to use a let statement because we don't even have a variable. What do we typically use? Let what?
X.
Let x equal a positive number. How about that? Okay, because that's what it said. Then it says the sum of that number and its reciprocal. Okay, so give me something. 1 over x. No, not a value. We don't even know what x is. 1 over x, the sum of the number and its reciprocal. The sum. Oh, thank you. X plus 1 over x. We need to set this equal to something. And typically, I mean, we want the sum, so just take the first letter. I mean, that's the easiest thing, right? The sum is equal to the number plus its reciprocal. Okay? So what we want to do is make sure that this sum is as small as possible. So we got to figure out what number is going to do that. So if I'm looking for a minimum, that means I'm going to need to take the derivative. Agree? Is this friendly form? How could I rewrite that in friendly form? X to the negative 1. So this is the same thing as x plus x to the negative first. So we're going to take the derivative. And when we take the derivative of s with respect to x, you don't want to write s prime. We're going to use the notation that we used when we were dealing with related rates. So what?
Oh, wait.
dx.
Oh, wait.
No, it refers to x, so ds, dx.
Yes, ds dx.
All right. My brain is
Yes,
programmed.
we are taking the derivative of the sum with respect to the variable x. Okay? That's okay. Yep. Okay, what's the derivative of x? 1. Okay, and when I take the derivative of x to the negative first, what is it? Negative x to the negative second. So can I write it as minus 1 over x squared? Okay, so when we are finding a minimum or a maximum, meaning we're solving, that means I need Shakespeare. Come on, yes, critical numbers.
Sorry, I was like.
Oh my.
I was starting to make a
Okay,
I was starting to like.
so I need this to be one quantity. So that means I need to get a common denominator. What is my common denominator? It is x squared. So I'm going to move this here. So this is going to be what is it? X squared minus 1 over x squared. Okay, and we're going to set that equal to 0. So what we have is a situation here that we've talked about a few times. I talked about it last class, where you would set the numerator and the denominator equal to 0 for those critical numbers. Okay? When I set the numerator equal to 0, first of all, let me factor that. X plus 1, x minus 1 is equal to 0, and this is over x squared. Okay, we have critical numbers or critical points where x is equal to, we have 3 of them. What are they? Negative 1, yep, 1, and 0. Okay, so when I go back to the problem, it says find a positive number, and we already talked about eliminating any values.
0. By 0.
Okay, by 0, and you said by negative 1, so that means we still need to make sure, okay, that 1 is a minimum.
Yes.
Right? Okay, so we want to test that. So when I put my value on the number line here, I'm just going to use 0 as a marker, even though it's not a critical number, and I'll put 1 right here. So I'm talking about before and after. You can't use 0. Why?
Because it's not a positive number.
Well, also, too, here's my question. When I'm testing these intervals, what am I testing in? Which function am I using? Am I using s equals? Am I using...
Yes.
Yeah, I'm using the derivative. Okay, so ds dx. Okay? And if I were to plug 0 in to use that on this interval, what happens when I plug 0 into the derivative? Yeah, it's over. You can't use it, right? So I need to pick something else. Does everybody understand what I'm saying? So let's, I don't know, pick 0.5. All we really want to see is what's the sign. So here we have 0.5 squared minus 1. Is this top going to be positive or negative? And what's always going to happen in the bottom? Yeah, so that means this is negative, so decreasing. All we're doing right now is verifying that 1 is a minimum. And it looks like it's headed that way, but I just need to double check. What do you want to plug in on the other side? Okay, what's going to happen? Yeah, it is positive. Okay, so you just tested just to be sure. Okay, so x being equal to 1 is our minimum. So x being equal to 1 would be that positive number. So you still need to state it. You would say that s, meaning our sum, has a relative min at x equals 1 because, this goes back to when we were testing before, ds dx changes from negative to positive. And here you would just say x is equal to 1. Okay, if they were asking you what is that number, x is equal to 1. Justification, right here. Okay, questions. This is a very simplistic answer. It's not, I mean, you have to give the calculus reasoning, but, okay. Questions? You sure? Okay. So here, in the second question, it says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. Okay, we know no river is straight, but we'll just deal with it. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so first of all, 2,400 feet of fencing. Wants to fence off a rectangular field. So that kind of gives me an idea of what the field's going to look like. So now I have an idea. I've got 2 possible formulas, right? We have perimeter and area. Okay, he needs no fence along the river. This is kind of important, I think. Dimensions of the field. Okay, give me some examples of dimensions. Like, what would you say? 5 by 7, yeah, 3 by 5, right? So you're going to need to give the dimensions like that, but we want the largest area. So someone tell me what's happening here. Largest, we want to maximize what? The area. So we're looking to maximize the area. So that means when we are taking the derivative of a formula, we're going to be taking the derivative of what kind of formula? The area. Okay. So let's deal with a couple of different things. First of all, we're going to draw a figure. So even though this is, we'll pretend like this is straight, this represents my river. Okay. And this guy wants to fence in a rectangular field. True? Okay. Now, we don't need fencing along the river, but when you put fencing here in this rectangular area, what would you call that in terms of a formula? Perimeter. Okay, so we're going to need the perimeter and the area formula. Does everybody see? So that way we're going to have a substitution. So what do you want to call these two sides?
Y.
Okay, if we call these both y, then this has to be x. Do we need an x here? Why? No fence here. Okay, no fence. Now, how much fencing does this guy have?
2400.
Okay. That's all he's got, so he wants to maximize it. Okay, he wants to maximize the amount of space that he can fence in with what he's got. He can't purchase anything else. So, what's a perimeter formula? Remind me. Perimeter. Just in general. Forget about this for 1 second. What's a perimeter formula? Add all the sides. So wouldn't it be 2x plus 2y is equal to p? Okay, but in this case, I don't have two x's. So this is going to be x plus 2y. What's the perimeter, though? Don't we know what it is? What he wants it to be? It's a 2400. So we have 2400, okay, is equal to x plus 2y. Now, I have a quick question. Is it possible that someone could have said that these are the x's and this is the y? It doesn't matter, right? Your dimensions are going to be something by something. So it doesn't make a difference. Okay. And we want to maximize the area. So we have area is equal to length times width, or in this case, x times y. Agree? Okay, so if you go back to the directions or the strategies at the top, it says that you can't have two variables. So that means I need to make a substitution. That's why this is important. So I need to use this to solve for either x or y. What do you want to solve for? Yeah, it's the easiest to solve for x. I don't have to divide. I won't have any fractions. So in this case, x will be equal to 2400 minus 2y. Everybody okay? So before I take the derivative, I need to make a substitution here. Okay? So, area is equal to what? 2400 minus 2y times y. Okay, if I know I'm going to have to take the derivative, do you want to use a product rule? No. What are you going to do first? Well, yeah, distribute. So area is equal to 2400 y minus 2y squared. Okay, this is just, isn't this easy to take the derivative of? Yeah, okay, first of all, what's the notation here? dA dy. We're taking the derivative of the area with respect to our y, okay, is equal to, what's the derivative of 2400 y? 2400 minus 4y. Okay, so here's my question. This is my derivative. What am I doing with it? What do we want to find?
The maximum area.
We want to maximize the area, so we want to know what our dimensions are going to be. Okay, so what do I do with this? This is a derivative. Set the derivative equal to 0. So we've got 2400 minus 4y is equal to 0. Add 4y. So y is equal to 600. Okay? What do I need to make sure of first before I proceed? Could I have made a mistake? I need to make sure that 600 is a max. How do I do that? Do the number line, okay? So here's my number line. Here's my 600. Where am I plugging these values back in? Yeah, into the derivative. So I've got dA dy here. What am I going to do? Where do I go? Pick a number? What about z? Can we pick 0? It's just linear, right? So what is this, positive or negative? Positive. That's nice and quick, right? If you want to pick 1,000,
Oh, I do.
okay, 4 times 1,000 is 4,000, right? 2,400 minus 4,000, negative. Yeah. So this is definitely a relative max. Agree?
Yeah.
Okay. So, couple things. First of all, I will need to give the justification. So, which test did we use? We used the first derivative test. So we're going to say, by the first derivative test, the area has a relative max at y is equal to 600, in this case it's feet. This is a word problem, we need to be specific. Because why? W-H-Y, not the letter Y. What she said. Okay, dA dy changes from positive to negative. Okay, so you're justifying what you did to say that 600 is a maximum. So, relative, excuse me. But what is it asking for? No. We need the dimensions. What are the dimensions? So we have we have 600 feet by what? How do I find it?
Plug 600 back into the original function.
Which one? I have two original functions. I heard area and then I heard perimeter. Yeah, wouldn't this be easier if I plugged this in right here? This is 2400 minus 2 times 600. So what is that, just 1200? Done. Okay, so one thing that we had to do was find the dimensions. This is kind of like a two-part problem, but we had to justify how we said, okay, this is a max. Okay, does anyone have any questions before we move to the next problem, which is our box problem here?